Sure. Oh, I'll keep this one. Okay, I'll go with this one. So this is, thank you. I'll take a deep breath. Hope you enjoyed that. And we're gonna see now, listen to the last session of the morning before we go off to lunch. I believe it's a very tasty lunch because I know John, Liad, and the credit team. Am I on this one or on this one? This one. Okay. So we're ready to go on. So we're gonna hear from Doron Zarchy from University of Luxembourg on Aggios, Scalable Aggregated-Based Voting. Thank you.
Thanks. Now it's different colors, I see. Okay, so just a minute. How can I control the? I think this controller doesn't work.
Can we put the slide itself?
Okay. So yeah, I'll talk about scalable aggregated-based voting. This project is part of the Pablo project, is a grant that is funded by the Luxembourgish research government. And yeah. So I'll not, perhaps this will be a little bit weird because I'm not speak specifically about scalable problems in blockchain, but scalability in general in votings. So there are many challenges in the current voting systems. We primarily vote for a representative who's supposed to represent us as people, but in most cases, once these people representative get into office, they tend to forget us and to do whatever they do for their own interests. When voting is held infrequently, then these representatives have enough time just to take care of themselves and not take care of the people. And this lack of accountability may cause many troubles, as everyone, I guess, knows. And there was an American businessman called Bernard Baruch who said that vote for the man who promises least, and he will be the least disappointed. So high-frequency voting is a concept, sort of hypothetical concept, where voting is held frequently, and then this allows people not just to vote for representative, but also to vote for, the policy that they want to have and be involved in the decision-making in general. And there are clear benefits to high-frequency voting. There is increased public engagement. People get more involved in what's happening in their community or in their country or in their company or whatever. There is enhanced accountability because if people vote frequently, then also the representatives or the directors have more urge to be aligned with the people's vote. It is empowering. People feel more empowered when their voices is held regularly. And it also increases happiness. There was empirical work that showed that in direct democracy, people feel happier and more stable. And there are not many examples, and the closest we can get is Switzerland, which holds referendums, and it held almost 600 referendums since the modern country was founded. And also, by the way, there is they maintain constantly their system, their voting system, and they offer bug bounties if people see some vulnerabilities and so on. So they really take it very seriously. So there are clear challenges to high-frequency voting. First, it requires, in the physical world, it requires lots of people to take care of it, both for setup, for monitoring, and for tallying the votes. And this is very resource intensive, so it seems like it's almost impossible to do it in the physical world. But also, if we do it electronically, then it's still very challenging, because if we do it without a trusted authority, such as in blockchain, then we'll need to get into consensus, and if we do it very frequently, then there might be security issues, and not talking about all the work that should be done by the verifiers and the validators. So we'll need, so perhaps there might be a different solution for this. And a straightforward solution will be aggregation-based voting. So in this kind of scenario, we have voters, and we have aggregators. And also we have this public bulletin board. So the voters vote, but instead of sending their votes to the public bulletin board, they send their votes to aggregators. These aggregators tally these votes, and so they tally. So for instance, it can be that, Alice says that she got 8 votes for Alice. I'm sorry, this aggregator says that she got 8 votes for Alice, 10 votes for Bob, and 7 votes for Charlie. And the other aggregator says, and other tally result. So this clearly is more scalable, because we don't need to count all the voters' votes, just check what the aggregators say. And then after the aggregators tally these votes, they send it to the blockchain, and or to another, whatever it is, and they verify and tally the results. But there are security challenges for this. There are many challenges, but I'll just pick about the main ones. Regarding voters' integrity, a malicious voter should not be able to vote to send its vote to more than one aggregator, because then its vote will be counted more than once. And also, a voter should not be able to send more than one vote to the same aggregator for the same reason, basically. A corrupted aggregator in this setting should not be able to corrupt the tally. So the system needs to provide guarantees that the aggregator did not change the tally. It should provide also a security that only registered voters voted. And it also needs to guarantee security against hypothetical collusion between corrupted voter and corrupted aggregator. So this should be strong enough to hold even collusions between a voter and an aggregator. So this was about the integrity. And regarding privacy, so third parties, so parties that are not the voter or the aggregator, should not be able to link between the voter's vote and the voters' identities. And an extra privacy, which I will not talk about it here, is also to provide privacy from the aggregator. So suppose there is a possibility that the aggregator itself does not know who voted for whom. It just knows the votes, but it cannot connect between the votes and the voters. Okay, so I'm going to present this voting system called Aggios. So Aggios has in aggregate-based voting, has these 3 parties. And we have voters, aggregators, and validators. So validators are basically what we saw before as the blockchain. Just third parties that can just check that everything goes correctly. So the voters send their vote through a secure channel. So we assume that there is a secure channel between the voters and the aggregators. The aggregators collect these votes and publish the tally. And to provide all the security that the security goals that we presented before, they need an accumulator, basically cryptographic accumulator, to ensure that the aggregation process was processed correctly. And the verifiers are, as we said, they're just third parties that can be anything and can just monitor the blockchain and see that everything went correctly. Okay, so what type of aggregate accumulator will it be? It will be accumulator of the following type. It will be a zero-knowledge proof that a subset of size T voted for A, a subset of size T2 voted for B, etc. And we also want to make sure that the union of all these subsets is equal to the set itself. Just a minute. Okay, so what current tools do we have from my checking? This is what I found. So I did not find actually a zero-knowledge proof for subset membership, but for multi-set membership. So it means that elements can occur. So it just showed that there is an accumulator and there is a zero-knowledge proof that shows that multiple elements are in the accumulator, but these elements can occur more than once in this accumulator. So what types of accumulators do we have? We have the most common used is Merkle trees with ZK snarks. But this is quite a heavy machinery, and it requires lots of constraints, even for algebraic hash functions. And the number of constraints that needed to be held just to check that all the elements are unique also increases the size of the circuit. Regarding RSA accumulators, this is less common, but this is actually an improvement over the Merkle trees. But the problem is just encoding the group operations over RSA group takes huge number of constraints. So this is also a little bit heavy. There were also improvements by Daniel et al. And Campanelli, which improved this asymptotics, but it's still quite heavy. And there is a line of work that I guess most of you here know, started from plookup, calc plus, and all the others, that they are based on lookup tables, and they are very efficient in terms of proving time and verification time, and proof size. But the problem is that they don't prove a subset, they prove multi-sets. So they don't prove that each element occurs only once, but there might be repetitions. So I'll just now define what a lookup table-based accumulator is, because this Aggios is based on this as well. So the vanilla definition of lookup tables is that given a collection of values Ci, which is simply a vector, which is called a lookup table also, and another vector that contains the values AIs, a lookup table argument says that all the elements in A also occurs in C. This is the vanilla definition. And a privacy-preserving lookup table, which is what is actually all this worked with, is that instead of having the vector itself, we are given a commitment to this vector. So we're given a commitment to a vector C, which is encoded as a polynomial. And we're also given a commitment to vector A, which is also encoded as a polynomial. And we need to show that A contains a subset of the elements in C. So there is no specific order, so the order of the elements can be different, and also the elements can repeat themselves. So this is the privacy-preserving variation. And now I'll just speak a little bit about calc and the follow-up papers. So we are given an trusted setup, and then we are given a vector, as I said before. So suppose this is the vector. So each vector can be encoded as a polynomial using a Lagrange interpolation. And then they defined an auxiliary polynomial, which is a polynomial that agrees on all indices in some subset. We can call it I. It agrees with the elements in C. So Ci agrees in all elements that are in C with the vector C. And in order to enforce this, they introduce this equation. They introduce the equation that Ci of x is equal Cx mod Zix, where Zix is the vanishing polynomial, so which is basically the roots of it's basically the product of all the roots of the polynomial Cx minus Cix. And in order to connect it with the looked up table, with the smaller vector, the prover has access to another polynomial, which is a mapping from one subgroup to another, let's say from V to I. And then they introduce a constraint that the polynomial of the smaller vector A is equal to the polynomial Ci when it is evaluated on the mapped values. So basically there is a mapping from each element in A to an element in Ci. Okay, so, and this work is an attempt to generalize it to multiple subsets. So I'll just present the definition. So here we are given functions f1 to fk. Each function is an invertible function over a field, and the prover has basically the same input. It has it is given the lookup table, and also there is a public commitment to this lookup table, and the prover now needs to publish not just one commitment to the small vector, but k commitments. So it produces k commitments that are associated with these k vectors. Each vector is associated with a subset of the voters you can think of, and also it gives the size of each vector publicly. And clearly, the size of all the subvectors needs to be equal to the size of the lookup table. So now the proving time is clearly not as efficient as we saw in calc, because in calc they really heavily rely on the fact that the smaller vector is much smaller than the lookup table, and so the proving time is linear in the smaller vector, and here the proving time will be linear in the size of the lookup table. The prover also provide a proof, which shows that every element in the lookup table has an associated element in one of the vectors that corresponds to the small looked up table. And this mapping is invertible, and it also uses one of these functions that I showed. So phi of C is equal to fj of A. So each subset has its own function that defines it. And we want to show that also that this mapping is one-to-one. So we don't want to have some repetitions. So I'll just go through this generalization, which is quite simple. through these examples. So if we just add more constraints, not just for one, but for instance, for two subvectors. So I just wrote it 2 times, but now instead of having just I, we have ij. So we have I1 and I2, ci1 and ci2. And if we just add this, then there can be clear intersections. So the vector ci1 has intersection with the vector ci2. So this is something that we want to prevent. Also, there might be elements that are not covered by all the subsets. So we want to have a cover, a full cover of the subsets that are induced by these polynomialsCij's. So for instance, here 20, the element 20 is not covered by any polynomial. So we add another constraint, which is that the polynomial of the lookup table is equal to the sum of all the auxiliary polynomials. So this will provide some constraint that will do several things. One, it will prevent intersections. So you can see here if we have like ci1, which is equal to this, and ci2, which is equal to this. Also, these vectors has been extended. So when ci1 does not agree with c, so we just add here 0. The reason for doing this is because we need to make sure that all the vectors has the same Lagrange basis if we add them up. So if we have 2 vectors, ci1 and ci2, and we sum them, then we don't get. And if there is an intersection, then if we sum the 2 vectors, we don't get the 3rd vector. So this is good because this is something that we want to prevent. Also, if we remove the previous constraints, we might end up with vectors that are not in the lookup table. So we have to keep both constraints. But still, there might be intersections because, for instance, if we have ci1 plus ci2, which is equal to c, we can actually have another vector ci3, which is just the same as c. So there might be, so these constraints still does not prevent this intersection. So we need just another check for this. And the verification is almost the same as there were in the previous works, just that we add another type of constraints that talks about the sum of the polynomials here. And the prover needs to provide this polynomial quotients the prover needs to provide commitment to the polynomial quotients for both constraints. And also we need to make sure that everything is one-to-one, so that each element in A is mapped to a unique element in one of the CIs. So instead of having this constraint in constraint 2, as you see, that uses this U, we replace it with a permutation with a grand product argument that was used in Plonk and in Sonic. So this will ensure that the mapping from A to CI is one-to-one. And the final, and still, as we said, there might still be intersections. So in order to prevent this, we just check that indeed the sum of all the subsets the sum of all the vectors AIs is equal to the size of the lookup table. So if we do all these checks, then we can guarantee that there is a one-to-one correspondence. As you can see, for each subvector, there is a different function that applies to the elements in the subvector. Okay, so I'll not, so just a little bit, I'll just speak quickly about the performance. The proving time is O of n because it works with all the elements, with all the elements in the lookup table. But the proof size and the verification size is linear in the number of subset, not in the number of all the elements. Okay, so now let's see how it works with a voting protocol. So in the voting protocol, we have a setup and 2 generators. And the voter publish a public voting key. So they have 2 pairs of public keys. They have public voting key and like the traditional PKI public key. So they publish this, and then they agree on canonical ordering of all the public keys, all the public voting keys. This is important for the registration process. So during registration, each voter selects their preferred aggregator. And this aggregator collects the request of all the voters which selected her as an aggregator. And this aggregator then sends the set of all the voters who selected this aggregator as representative. So it's basically it sends the set of indices of these voters according to this ordered vector. The voters computes compress polynomial commitment only to their public voting key. And each voter computes its own polynomial commitment, and they send it to the aggregator, which aggregates it. And this aggregator gets a polynomial commitment that represent the set of all voters that selected this aggregator as their representative. And they send it, the aggregator blinds it and send it to the blockchain. And in the blockchain, they can verify that this is a correct polynomial using the public setup. They can check this. So now each voter has a proof that it corresponds to some aggregator. Now, for the voting, the voters compute. First they select their preferred choice, and then they compute a ballot using the secret voting key and the vote. So this 1 over VI is what I showed before as these functions. So these functions are very simple. This can be just exponentiation or an inverse of an element. But yeah, but we needed this extra function just to apply this to the ballots, and then it needs to, using these ballots, the aggregator aggregates all these ballots and creates a polynomial commitment. So the polynomial commitment is simply the sum of all these small polynomial commitments that are associated, which is with each of these voters. And so it computes the polynomial commitments for each subset and send it to the bulletin board. I'm sorry. Before it sends it to the bulletin board, it send these commitments to the voters with a proof of inclusion. So the voters can also check that this was computed correctly, just to make sure that they were not ignored. The voter signs this using aggregatable signature. And after that, the aggregator can compute the proof. They can compute this cryptographic proof using accumulator. Okay, well, I'll finish very quickly. And also it sends the results, and the third parties can verify the signatures and the result, and check that everything went correctly. So there should be also mechanism to handle irresponsiveness. So the voters might not respond, or the aggregators might not respond, but we assume that they have incentive to respond because it's being rated and there is a proof if they don't respond. And just possible improvements is just to reduce number of rounds, do hierarchical aggregation, and also have another mechanism that keep the vote private from these aggregators. That's it.
Thank you, Doron. We have time for one question.
Sorry to hog the questions. How does a voter tell that their vote has been included?
What?
How does a voter tell that their vote has been included?
Just a KZG proof, simple KZG proof of inclusion.
Okay, thanks.
Okay. That was short. Does anybody have any other quick question? Or? Okay. So let's thank again the speaker. Great. That was the morning session of the first day. We touched a bit on scale in the context of how to improve, make faster, more efficient kind of schemes, talked a bit about privacy in applications. We'll see more of this in this afternoon. Go enjoy lunch. I think we have an hour and a half until 2:30, if I'm not mistaken.